Okay, the next law we're going to look at is called Gay-Lussac's law. And Gay-Lussac's law is going to be looking at what happens when the volume is held constant. So on your back of your reference table, you have the combined gas law. Here, I just took the volume piece out of it because remember when something is held constant, we can eliminate it from the equation. So we had the V1 and V2 here, but since in a question involving Gay-Lussac's law, it'll be constant, we could remove it. So our question setup would become P1 over T1 equals P2 over T2. Remember that this is a division, P divided by T, so this is a direct relationship. When it's direct, you divide. So when the temperature increases, pressure increases. And if temperature were to go down, pressure would go down. So similar to the last case that we looked at with Charles' law, we're going to show you again another example of a direct relationship depicted in a graph. So as the temperature goes up, the pressure goes up. And as temperature goes down, the pressure goes down. So let's get to an example. What is the pressure inside a rigid cylinder that starts at 25 degrees Celsius and 1.2 atmospheres if the temperature is raised to 100 degrees Celsius? So again, we got to mark up our text. We have Celsius values here and here. And we have atmospheres, which are going to represent our pressure. Question also says, what is the pressure? So we're going to be looking for a pressure value as well. Since the cylinder is rigid, it's not changing shape, we could assume that our volume is going to be held constant. So we have a relationship that we could look here. Our combined gas law. And what we're going to be doing is we're now going to say, okay, we have a rigid cylinder. The volume is not changing. We could eliminate it from the equation. So we have P1 over T1 equals, oh, that's a bad one. P1 over T1 equals P2 over T2. Now, remember that when we have a value in Celsius, we can't leave it in Celsius. We must convert all of our Celsius values into kelvins. Otherwise, the math will not work out. So when we set up our variables, we could say okay, so our initial temperature is 25 degrees Celsius. So adding 273 to that to convert it into Kelvin gives me 298 kelvins. And our second temperature is 100 degrees Celsius, which if you add 273 to it, we would get 373 kelvins. The initial pressure is starting at 1.2 atmospheres. So we'll put that as P1. We want to know what's the final pressure. So plugging all of our variables into the equation, P1 is 1.2 over T1 is 298 equals P2 is X and T2 is 373. We cross multiply to figure out what the value of X should be, and we should get around 1.5 atmospheres. Okay, here's one more example. We have a cylinder with a movable piston contains a sample of gas having a volume of 6.0 liters at 298 kelvins and 1.0 atmosphere. What is the volume of the sample after the gas is heated to 303 kelvins while the pressure is held at 1 atmosphere? So since it's saying that it's held, the pressure is constant. If we say that it's held at 1 atmosphere or it's staying the same, that means that it's constant. So when we look at our combined gas law, P1 V1 over T1 equals P2 V2 over T2. If pressure is being held constant, we can eliminate it from the equation. So we have V1 over T1 equals V2 over T2 is what we're going to be looking at in this question. Let's look at our variables. Let's set them up. So V1. Okay, so it has a volume of 6 liters at 298. So it starts out as 6 liters at a temperature of 298 Kelvin. And then we see that the gas is heated to 303 kelvins. So that's the new temperature. And we're trying to figure out, well, what is the new volume going to be? So plugging this into our equation over here, we have 6 over 298 equals X over 303. Cross multiply. You end up with about 6.1 liter. So in that ballpark, you are good. Okay, so just want to give you a real life connection. Why are we talking about all this gas law stuff? So let's talk a little bit about tire pressure. So in the wintertime, we know that it gets colder outside, meaning the temperature goes down. So if the temperature goes down based on what we just talked about with Gay-Lussac's law, what should happen to the pressure? Well, since they have a direct relationship, we should understand that the pressure will go down, which means that there's going to be less collisions with the molecules within the gas tire. So remember that pressure is related to, you feel pressure because of the collisions within the container. So if we have the particles moving faster because it's a hotter temperature, they're going to collide more with the container. You'll feel more pressure. But on a colder day, when the temperature goes down, there's less collisions with the walls of the container because the particles are now moving slower. So we say, why do you think it's recommended that you check the tire pressure? Well, that's because if the temperature is going to be hot or it's going to be cold, your temperatures could inflate or deflate. And you'll notice that sometimes, like your car will, you guys will have like sensors in the cars now that will come up saying, okay, your tire pressure is low. You should make sure that you fill your tires up. So now what we want to do is we just want to combine all three gas laws together. We looked at Boyle's law, we looked at Charles' law, we looked at Gay-Lussac. The Regents is never going to say, oh, using Boyle's law, do this. They just want you to understand what to do when in a question they tell you one of the variables is constant. We talked about, well, if one of the variables is constant, just put your finger over it and remove it from the equation. Sometimes nothing is constant except the number of molecules. So sometimes we're going to have to plug in the p-value, the v-value, and the t-value. So make like a huge cross multiplication problem. So remember, Boyle's law is when temperature is held constant. When the temperature can be ignored in the combined gas law equation, we just crossed out our t's. We looked at Charles' law, where pressure is held constant, and then we just crossed out the p's. And then we looked at where volume is held constant, and we crossed out the v's. So let's look at a problem. A 15-liter cylinder of gas of 4.8 atmosphere pressure at 25 degrees Celsius is heated to 75 degrees Celsius and compressed to 17 atmospheres. What is the new volume? So many numbers. We want to just make sure we're keeping track of all of our variables, and that when we do look at temperature, we want to make sure our temperatures are in Kelvin. Okay, so here's our equation. P1 V1 over T1 equals P2 V2 over T2. Let's set everything up. P1 V1 T1 P2 V2 T2. So the initial pressure is 4.8 atmospheres. It's compressed to 17 atmospheres, so that's the second pressure. The initial volume is 15 liters. They want to know what's the new volume. It's a V. Yes, that's a V. Sorry. Okay, the initial temperature is 25, but remember that we cannot ever have a gas law problem with temperatures in Celsius. So our T1 is 298 kelvins, and T2, it tells us it's at 75 degrees Celsius. So add 273 to that, and you get 348 kelvins. So let's set it up. All right, P1 comes here. So we have 4.8. I'm going to omit the units for the moment. Times 15 over 298 equals P2, which is 17, times V2 over T2, which is 348. It might be easier for you at this point to simplify. You might want to multiply these first. I just multiply everything into one big cross multiplication problem. So 4.8 times 15 times 348 equals 17x times 298. So 4.8 times 15 times 348 equals 298 times 17 times V2. So we do that. So simplifying that, when we multiply 4.8 times 15 times 348, we get 25,056 equals 298 times 17 times V2. When I multiply 298 times 17, I get 5,066 V2. Same as if this was a regular cross multiplication problem. We need to make sure that we get x all by itself. So Here I would divide by 5,066. And when you do that, you should get that V2 is about 4.9 liters. Okay, one more example. At 25 degrees Celsius, gas in a rigid cylinder with a movable piston has a volume of 145 milliliters, a pressure of 125 kilopascals. Then the gas is compressed, pushed down to a volume of 80 milliliters. What is the new pressure of the gas if the temperature is held at 25? So, remember this, the temperature is held. What does that mean when the temperature is held constant? Oh yes, we don't need to include it in our equation. So P1V1 over T1 equals P2V2 over T2. Goodbye T. We don't need the temperature because it's being held constant. So, I mean, you could put the numbers in, you're going to get the same result, but why do more math if you don't have to? So, our equation is P1V1 equals P2V2. Again, we can set up our variables. So, we are at a pressure of 125 kPa, kilopascals, and a volume of 145 milliliters. The new volume is 80. So they want to know what's the new pressure, X. So plug everything in. 125 times V1 is 145 equals P2 is X and V2 is 80. And then you're just going to solve for X the way that you would by cross multiplying, and we should get the new pressure. So P2 should end up being around 226.5 atmospheres. And this should make sense to you because we're looking at what's happening to our volume is going down. The volume was at 145 and it went to 80. So remember that if volume goes down, pressure is inverse, it should go up. So if the pressure was at 125, our new pressure should be something higher. So 226 makes sense